Hello students, and welcome to the pre-lab video for Boyle's Law. You know, certain gases at room temperature and pressure behave as ideal gases, we say. And usually these are the gases composed of the elements on the right side of the periodic table. But I tell you, air at room temperature and pressure behaves pretty well like an ideal gas. And what does that mean? That means that the state variables, say the volume the gas occupies, the pressure of the gas, and the temperature, they are related to one another through a very simple equation of state, we say. And that equation of state is the ideal gas law. And we're going to study a certain aspect of that equation of state today. It turns out if I have a constant amount of ideal gas at constant temperature, we find the pressure is inversely proportional to the volume, and we refer to that as Boyle's law. So in other words, if I were to lower the pressure I were to increase the volume, I would lower the pressure of the air in this balloon. So we're going to experimentally confirm Boyle's law for a relatively small amount of air in this lab today using a very simple apparatus we call a Boyle's law apparatus. And I want to demonstrate that to you and show you how to set it up and use it and get good results. So this is the apparatus here, and it's just a syringe, very simple thing, and there's a tube on the end there, and there's a little clip you can use to close off the syringe, and it reports volume in cubic centimeters here. So to start this experiment, you would open this in and you would pull out the plunger until you're right at the 10 cubic centimeter mark. That's a good starting point. So that would be the original volume for your gas, and then you're going to close it off so the amount of gas will be constant, and of course it's at room temperature. The temperature will be constant as well. And then notice there's a little hanger on the apparatus, and it hangs down like that. And then you want to put it on a lab stand with a little burette clamp like this. And you want to make sure the burette clamp is right underneath the little collar at the top. And you want to just tighten it up enough to hold it there and not necessarily deform the tube itself. So there I have it, and notice I have it so that I can still see the scale there in cubic centimeters as the volume changes. So we're going to report our initial pressure there, our initial volume there, and it's at atmospheric pressure right now. We're going to change the pressure. We're going to increase it, and it's going to decrease the volume. How are we going to do that? We're going to take a mass hanger here and hang from that little hanger on the apparatus there, and we're going to add mass to it that will generate a force across the cross-sectional area of the syringe, which will give us a pressure. So you want to use as long a mass hanger as you possibly can so we can get as many data points as possible. So I'm going to start by adding, say, 500 grams like this, and you'll notice the syringe came down, the volume decreased. So I would report my new volume, and I would report the mass I have on the hanger at this moment. I would continue, add another mass, the volume will further decrease. I would record that, record my new mass, and I would continue to do this. You want as many data points as you can get on the hanger, so I might try adding 2 smaller masses. I'll get still a decrease in the volume. And you want to continue until you get the hanger completely full of mass. So you will have these data points, masses on the hanger, total mass on the hanger, and volume. So now we want to convert the weight on the hanger, obviously, to a pressure, and I'll show you how you do that. So it's easy enough to convert the mass to a weight in newtons, but we need an area so that we can compute a pressure. So you want to open up the opening on the bottom of the syringe, pull out the plunger very carefully, like this. And then you'll take your vernier caliper and you'll measure the diameter of the syringe like that. Most of these are about 1 centimeter, we've found. And with that diameter, you can compute the cross-sectional area of the syringe itself, and then with all your weights, you can compute a pressure, a force divided by that area. And you'll have to be careful to convert everything to SI units for this lab. So the ultimate goal is to plot pressure versus one own volume, and it's easier, it's more convenient to plot the log of pressure versus the log of volume, fit it to a curve, and see if you can find out what the constant would be in the ideal gas law. And it turns out the constant will involve the amount of gas, the constant room temperature, and the universal gas constant. So the point of the lab is to compute an estimate, use your data, use the curve fit to compute an estimate for the universal gas constant in SI units. And you'll compare it with the known and compute a percent error. Obviously, it's easy to get room temperature, but you might think about how you would get the amount of gas you initially had in the cylinder in moles. So you're going to have 10 cubic centimeters. You will assume it's nitrogen gas. You'll probably need the molecular weight for nitrogen, Avogadro's number, and maybe even the density of air at room temperature. You'll have to use those things to compute the number of moles that you had at the start, which remain constant throughout the lab. So with that, with your curve fit and constant temperature, you can easily get a very good value for the gas constant. You should find it's about 8.134 joule per mole Kelvin. And then you would have completed the lab with success. So very easy lab, not much equipment, easy to get through it and get very good results if you pay attention to the things I told you here and do the setup and such correctly. So I look forward to seeing you in the Boyles Law Lab.